In previous lessons, we've been working on solving different types of functions, mainly linears and absolute values. Today we're going to look at how we can solve quadratic functions by various methods. And the first one we're going to look at is solving it by undoing. And you've done this method in the past, so let's do a quick review. Here we have 3 times the quantity a minus 2 squared equals 21. We want to undo the equation to solve for a. So as we take a look at the equation, we're going to think about what operations we see. So I see 3 times. Well, in order to undo multiplication, we can divide. So we're going to divide each side of the equation by 3. That will give us the quantity a minus 2 squared equals 7. So if something is squared, we have to think how we would undo that. Typically, we would take the square root. So we would square root each side. So we can see that we've got the square root of 7, and we've been working on simplifying our radicals, and 7 is not a perfect square, nor does it have any perfect square factors, so we're going to leave that as is. On the left-hand side, we've got the square root of the quantity a minus 2 squared. So we have to think back to what we've done in the past. Whenever we've had to take the square root of something squared, what resulted? So let's take a moment to review what we've done in the past, looking at these functions, the graph, and the table. So taking the square root of something squared results in the following. Here's our graph and here's our table. Hopefully this is familiar to you based on seeing the shape of the graph and what we're seeing with our inputs and outputs in the table. We know that this represents the absolute value function. It's measuring the distance from 0. So in our equation, we have now the absolute value of a minus 2 equals the square root of 7. And we can travel this distance from 0 to the left and right of the number line. So we're going to set up traveling both distances. Now we worked on solving absolute value functions before. Again, we want to undo it to get the variable alone. So if we look at the left, the first step here would be undoing the multiplications. We could divide each side by 1. On the right, similarly, we would divide each side by a positive 1 versus the left's negative 1. So that would bring us to here. And then we can see that we've got the subtraction. So in order to undo the subtraction, we would add 2 to each side. And so we have to ask ourselves, since we're adding 2 to each side, this will make the 0, so we'll have a equals. Again, this makes the 0, so we'll have a equals. Are 2 and the square root of 7 like terms that we can combine? One is underneath the radical and one is not. Therefore, we cannot combine them, so we're going to have to write it as 2 minus the square root of 7 and 2 plus the square root of 7. Or we could write it as the square root of 7 plus 2, or negative square root of 7 and opposite of the square root of 7 plus 2 as well. So these represent our 2 potential solutions for our equation. Now, as we've done in the past, we can check our solutions by substituting them back into the original equation to make sure they're balanced. And so that's what we're going to do next. So we're going to check them. We're going to substitute in to the original function. So we're taking our value for a and substituting it into the original, and our other value for a is substituting for the original, and simplifying according to our order of operations. Well, within the parentheses is where we have to begin, and we see we have a positive 2 and a negative 2, which makes a 0. Same for this check. So now we have 3 times the quantity, the opposite of the square root of 7 squared. Well, if I'm squaring it, I'm taking a negative times a negative, which is a positive. And if I'm squaring a square root, we know they undo each other. So that will give us a 7. 3 times 7 is 21. Again, we had that 0 come here, so we've got the square root of 7 squared. Those undo each other, so we have 7. 3 times 7 is 21. So both answers check out, so we have the 2 possible solutions. Now, if you notice, the only difference was going to the left and right that distance. So instead of writing them as 2 separate results, which is fine, there's nothing wrong with that, oftentimes you'll see mathematicians combine them into one representation, saying we're writing 2 to the right and left, the square root of 7. These are equivalent formats to the results, showing you the 2 possible solutions you can get for your quadratic. Let's try another. Here we have 4c squared plus 9 equals a negative 17. Again, we're trying to undo the equation to get c alone. So normally the operations that we do last, we would undo it first. So here we can see that we're adding 9, so in order to undo that, let's subtract 9. So this will make the 0 on the left, and we'll have a negative 26 on the right of our equal sign. Again, trying to undo to get c alone, well, we see it's 4 times c squared. So to undo that multiplication, we can divide each side by 4. Well, on the left-hand side, we know 4 divided by 4 is 1, so we'll have c squared. And then I have negative 26 divided by 4. Well, 26 and 4 have a common factor of 2, so if I divide it by 2, I'll have a negative 13 over 2. We're getting closer to getting c alone, but it's c squared equals a negative 13 halves. Well, again, how do you undo something that's squared? You square root it. So we'll square root each side of the equation. And we know the square root of c squared is the absolute value of c. And then I have the square root of a negative 13 halves. Again, working with simplifying our radicals, we want to see, so 13 and 2 have any common factors we can divide out. If so, we'll take care of that. If not, let's see if we can simplify the numerator and the denominator separately. So we're going to think of this as the negative 13. And so negative 13 comes from 13 times a negative 1. So we're going to rewrite that numerator as the square root of 13 times the square root of negative 1 over our denominator, the square root of 2. Now 13 is not a perfect square, nor does it have any perfect square factors, so that's already simplified. 2 is not a perfect square and does not have any perfect square factors, so that is simplified. The square root of negative 1. Well, we learned previously that the square root of negative 1 is defined as I. So we're going to rewrite that with our I. So we have I times the square root of 13 over 2. Now we talked about before, we don't typically have square roots in the denominator. They're irrational numbers. We want to rationalize that denominator. So since this is the problem, we're going to multiply the numerator and denominator by a value of 1 to make sense of it. So let's multiply the numerator and denominator by the square root of 2. So again, this is a value of 1. We're not changing the value of your distance here, just how we're writing it. And again, we multiply fractions by going across. So the parts underneath the radical can get multiplied together. So in our numerator, we'll have I times the square root of 26. Then we'll do our denominator. Well, 2 times 2, that's 4. So we have the square root of 4 in the denominator. We know that 4 is a perfect square, and the value of the square root of 4 is 2. So it says the absolute value of c is equal to I times the square root of 26 divided by 2. Well, the distance from 0 is the definition from absolute value, so we have to go left and right our distance from 0. And this is possible for a distance. So we know how to represent going to the left and going to the right. From 0, our distance that's given. So now we just have to undo going to the left and right. Well, this is negative 1 times c. Well, to undo that multiplication, we'll divide by negative 1. So we're taking the opposite of what we had before. Since we're multiplying by 1, we could divide by 1. That's not going to change what we have for our distance. So it appears that we have two possible solutions. We have a negative I times the square root of 26 over 2, and then I times the square root of 26 over 2. We can check these like we've done before for our previous problems, substituting them into the original equation, and we should get back a negative 17, which is what we started with. Again, mathematicians, because we compare and see that one is a negative and one is a positive, they like to condense. Therefore, you may see representations of your solutions written like this, saying that c is equal to going to the left and right, your distance, I times the square root of 26 divided by 2. So we can undo quadratic functions just like we've undone our linears and absolute value equations. We can check the results for the equations the same way that we've done for our linear and absolute values, substituting in our values for the variables and making sure that they're balanced. So let's take a look at another quadratic function. Here we have negative 3f squared plus 3f plus 90 equals 0. So if we look at this function, notice how it's a little bit different than the prior two. This one's not set up nicely to undo, because if we subtracted 90, we'd have negative 3f squared plus 3f equals negative 90. And because we have the f squared and f, we can't really undo that by division and isolate one of those variables and have an f equals like we were doing before. So undoing is not a great method for this quadratic equation that we have. So perhaps there's other methods that we could use in our past to simplify the polynomial that we have here for our quadratic function and solve for that variable for f. Well, we've done some factoring, right? Simplifying our polynomials, and when we've done that, for our factoring, we've looked to see, do they have a greatest common factor that you can divide out from every single term? In this case, we can see that 3 is a factor of each of those terms to your quadratic polynomial. My leading coefficient is negative, and typically when we are factoring, we don't like having negative leading coefficients, so why don't we divide everything by a negative 3 for the greatest common factor? Now, factoring an equation, we just have to make sure that we're keeping the equation present. So before we were doing expressions where it wasn't equal to a value, here we do, so we have to maintain that. So here's our greatest common factor. So like before, we're going to focus with what we have here on the inside of the parentheses. So we want to think about that leading coefficient, which is now a 1, and that constant. And we're going to think what times what gives us their product, negative 30. And what plus what gives us the sum, for your middle term here, a negative 1. Well, I know that if I multiply to get 30 and add to get a negative 1, I'd have to use numbers that are very close to each other. We could use a negative 6 and a positive 5 to accomplish that. So we can rewrite this with our 4 terms using our patterns that we had before. We like factoring quadratics with 4 terms because we can look at them in pairs and divide out the pair's greatest common factor. So in this first pair here, we could divide out an f. The second pair here, we could divide out a 5. So here's our greatest common for the f and the greatest common factor of the 5. And notice when we're factoring here by the groups, we're looking to see, are they being multiplied by the same amount, which is f minus 6. So we know that it factors into f minus 6 times f plus 5. Don't forget, we still had the greatest common factor of negative 3 from the start. So here we took our polynomial and put it in factored form. This is an equation though, so we have to solve for f. And we know that multiplication is holding these 3 items together. Well, how do you undo multiplication? You can divide. So let's divide each side of our equation by negative 3. Well, negative 3 divided by negative 3, that's a 1. 0 divided by negative 3, that is 0. So we're one step closer to solving our equation. So again, we've got multiplication going on, and we're multiplying 2 items together to end up with 0. You know from in the past that when you multiply items together, the only way you can end up with 0 is if one of those items is 0. Well, we don't know which one is the 0, so we test both. We're going to say, okay, what if f minus 6 was equal to 0? Can we solve for f? If f plus 5 was equal to 0, can we solve for f? So we're going to set up those 2 scenarios. Well, if f minus 6 equals 0, to undo this, we could add 6 to each side. So f would equal 6. If f plus 5 equals 0, to undo this, we could subtract 5 from each side. Therefore, f equals negative 5. Again, to verify that these are the correct solutions to the equation, we'll take each one and substitute them into the original and make sure it's balanced, giving us back the 0 that we started with. So as you can see, when we take the 6 and substitute into the original equation, we do get back the 0 that we started with. When we substitute the negative 5 into the original equation, we do get back the 0 that we started with. So this has two potential answers. F could be 6 or it could be negative 5. Let's try one more. So here we've got 2h squared minus 4h minus 8 equals a negative h squared plus h. So again, looking at this quadratic equation, we can see that the left-hand side is simplified, the right-hand side is simplified. However, when we were working with the quadratics before, we had basically all of the variables and like terms were combined on one side of the equation, and it typically equaled a value. So we want the same thing to happen here. We want to combine our like terms. So let's put the h squareds together here on the left, and the h's as well on the left. So to undo a negative h squared, we can add it. To undo a positive h, we can subtract it. So now all the like terms are combined, and notice we have 3h squared minus 5h minus 8 equals 0. This is very similar to the last problem that we have. It's set up nicely to see if we can factor it versus undo it, because we have the h squared and the h here. So again, when we're factoring, we look at all the terms and say, is there something in common other than 1 that you can divide out from every single term? And as I look at these three terms here, they don't have anything in common that we can divide out, so no greatest common factor. So then we implement our pattern. We take the leading coefficient times the constant. So what times what gives us negative 24, and what plus what gives us a negative 5. Again, these numbers should be close together. Thinking about 24 and adding the 5, the numbers 3 and 8 come to mind. Well, in order to make both of those true, the 8 would have to be negative and the 3 would have to be positive. So I'm just going to rewrite my quadratic equation with my 4 terms to help me with the factoring. So here we've got our negative 8h, here we've got our positive 3h. Well, we like having 4 terms when factoring because we can split them into pairs and look at what's the greatest common factor for that pair. So this first pair here has a greatest common factor of h. The second pair here just has a greatest common factor of 1. So I'd have h times 3h minus 8 and 1 times 3h minus 8. Notice how they're both being multiplied by the same amount. So our factors would be 3h minus 8 times h plus 1. Remember, this is the equation, so we keep that equation how it's equal to 0. So we're trying to undo this for h, and again, we have multiplication going on here. And since we're multiplying to end up with 0, that means one of these has to have a value for 0. So we're going to solve each scenario. We want to solve 3h minus 8 equals 0, and also h plus 1 equals 0. Well, h plus 1 equals 0, we can undo this pretty easily by subtracting 1 from each side. So we know h equals negative 1. 3h minus 8 equals 0, we'd have to add 8 each side and then divide by 3, so h would equal 8/3. Again, these are two possible values for h that we think will make the equation true at the top. Again, the way that we can check is take each value for h, substitute it into the original equation, and see what transpires. Again, we want those equations to be balanced. Well, by substituting in the 8/3, we can see by simplifying based on our order of operations, it's balanced. The left-hand side of the equation is equivalent to the right-hand side of the equation. By substituting negative 1 into the original equation, again, we can see that it's balanced. The left hand of the equation equals the right-hand side of the equation. Therefore, we have two possible solutions for our quadratic equation we were solving for. H equals negative 1 and h equals 8/3.